All right, hello everyone. Thank you very much for joining us today for our live question and answer session. My name is Matthew, and I will be facilitating the session, getting your questions to Professor Impey. Alexander's helping us out behind the scenes, and Chris, why don't you go ahead and say hello, and we'll get started.
Okay, welcome everyone to a live Q&A session for the online classes, and the floor is open for your questions.
Thank you very much. The first question is from Geeta, who would like to know if you can talk about fractal dimensions which may exist in a black hole. Is this a thing that you've heard about, or is this not something that is part of mainstream science?
It sounds a little non-mainstream to me. So fractal dimensions do arise in astronomy in a couple of contexts, but not very well, to my knowledge, in black hole. The only potential for that is in the holographic idea of black holes, where information is potentially stored at the event horizon. It's a speculative extension of standard black hole theory. And I suppose you could assign a fractal dimension to the event horizon of a black hole in principle. Fractal, in general, in a mathematical sense, means scale-free phenomena, so phenomena that appear at a variety of range of scales with equal manifestation or strength. And black holes don't really fit the bill for that because they have an event horizon of a particular size and a mass of a particular amount. The only fractal incidence otherwise in cosmology and astronomy is in the dimensionality of large-scale structure in the universe, where structures form on various scales beyond that of galaxies, clusters, superclusters, and so on. And if you actually look at the fractal dimension of the clustering of galaxies, it's an interesting number. It's about 1.7, which is midway between strings or one-dimensional objects and sheets or two-dimensional objects. And the university does have self-similar structure or fractal structure on about 3 or 4 orders of magnitude of scales. But otherwise, fractals don't really apply to black holes.
All right, thank you very much. The next question is from Ethan, who would like to know if you can talk a little bit about the difference between causation and correlation, and why is that important for science, for cosmology, for simultaneity.
Sure, causation and correlation are similar sounding words, but actually very different in terms of their importance in the epistemology of science, or how science works. So it's an important question, and it goes far beyond astronomy, of course. So I would say it's easier to start with correlation. Correlation is a way that scientists of all kinds, including astronomers, try to look for patterns in the natural world. They might measure 2 different attributes of a class of objects like black holes or galaxies, or it could apply to biology even, or geology, other sciences, and look for correlations. And that means one quantity is related to the other. It could be a linear correlation or a nonlinear correlation going as a higher power. And when that happens, and you put the 2 quantities on a graph and they're not a scatter plot, that tells you something's going on when 2 things are correlated. Sometimes the correlations might be trivial. The area and the volume of an object are correlated with their linear dimension, because that's just scaling in mathematics. Regardless of the actual shape, there would be a correlation. So some correlations are trivial, but some are more profound, such as when 2 parameters that you don't anticipate being related to each other show to be correlated. The distinction between correlation and causation is, of course, that causation is a much stronger word in science theory. It means that A causes B, or something that you observe has an underlying cause that you can identify. And that's trickier in science, because inferring causation from correlation relies on you having a mechanism for the causation. Correlation is just a correlation. It might have no physical meaning. It might even be a coincidence sometimes. But causation implies a physical mechanism for A being related to B, and A causing B, or B causing A. So a lot of science falls at the point of demonstrating causation rather than just correlation. And so this distinction is actually a very important thing. And also, you can be fooled. You can be fooled by a correlation that has no causation associated with it, which means that you've not found any fundamental physical principle about the universe. You've just seen two things that just happen to be related to each other.
All right, thank you very much. The next question is from one of our live viewers. Robert would like to know if there are any new LIGO results and what's going on with that project currently.
Yes, LIGO is announcing results and publishing papers pretty steadily, one every roughly 3 or 4 weeks, pretty much. And so they've now gone up to about a dozen events that they've detected with LIGO in 2.5 years, pretty much. It's had some downtime since it made its first discovery. And these are a mixture of black hole mergers and neutron star mergers. They've never actually seen a black hole neutron star event, which they would anticipate at some point. And LIGO is also now in a phase of refurbishing itself, getting increased sensitivity, perhaps gaining a factor of 2 in sensitivity, they hope. And also LIGO is preparing to be part of a much larger network of gravitational wave detectors. So LIGO has also already done some coordinated observations with Virgo, which is the European gravity wave detector. And within a year and a half, LIGO and Virgo will be able to work with a Japanese gravity wave detector, not quite as good sensitivity, and there's one in India that's coming online. And when you have a network of these devices, of course LIGO consists of 2, then you can pinpoint the position of the event much more accurately in the sky, which helps the optical astronomers or other astronomers at other wavelengths to pinpoint the object behind the event. With increased sensitivity, in its next science run, LIGO is hoping for an event per week rather than about 1 per month, which is what they've had so far, actually a bit less than 1 per month. So this will be sort of almost industrial scale gravitational wave detection within a year or so. Very exciting.
Thank you. The next question is from Arian C, who would like to know, can black holes destroy information, or do they just trap it in their event horizon?
This is a matter of some great speculation among black hole theorists. I would say amongst observers too, except there is no way astronomers have figured out how to test these ideas. So at the moment we're still in the realm of theory and speculation. The question arises from what's called the information paradox, where black holes have very high entropy or disorder, and it appears that things that fall inside them are hidden from view, and so you lose all discrimination on what went into a black hole information, rocks, particles, missing socks, whatever. And the contradiction comes because in quantum theory, particle interactions should be symmetric in time, and so as particles disappear into a black hole, their information should not be lost at the level of quantum events. That's the paradox in a nutshell. The get around of the paradox is that maybe the information isn't completely destroyed. Maybe in the asymptotically slowing time, as seen from the outside of an object or information falling into the black hole, the information is essentially trapped on the event horizon, sort of like in a spider web. And that's the holographic principle, pretty much the way it's been framed by theorists. And it's a sort of get around to the loss of information in a black hole. The question then becomes is, if the information is not inspectable or extractable, then it's a little bit moot to say that it's coded on the event horizon if there's no way to inspect it. To all intents and purposes, the event horizon is still an information barrier or membrane. So it's not even clear whether this clever idea has any meaning, because if the information is still unextractable, then it doesn't really matter what clever artifice you've devised to say that the information isn't really lost, because it's moot. So I think it's a matter of some argument amongst theorists whether there's any play here at all.
All right, the next question is from Taha Acoustica, who would like to know, how do you think the James Webb Space Telescope will change the way we deal with big data?
Yeah, the James Webb Space Telescope, in and of itself, will not actually transform the big data situation. And that's in part because the data rate for James Webb is not dramatically larger than any other space-based observatory. It does have bigger detectors, and it does have a higher data rate than Hubble Space Telescope or Chandra or Spitz or the other great observatories that preceded it, but not by more than a factor of a couple. And in fact, the data rates for returning data from this long distance from the Earth, this million kilometers from the Earth at the Lagrange point, is quite limited. So that the interplanetary internet does not work at extremely high speed or bandwidth. So JWST, almost by design, is not going to push big data boundaries. The project that's on the horizon in astronomy is the LSST, the Large Synoptic Survey Telescope, last year renamed the Vera C. Rubin Observatory, down in Chile. That's using one of our large mirrors made at the Mirror Lab, designed to do a sky survey of the visible sky from Chile down to Hubble depth about every 3 nights. And that data rate is 20 or 30 terabytes a night, and that's a pretty prodigious data rate to digest and extract catalogs from and put online and make available to all researchers. So LSST is the project of the near horizon that's going to push data limits rather than JWST.
The next question is from one of our live viewers. Why are no missions to Titan and Enceladus being planned right now?
Actually, they are. Titan has always been of interest to planetary scientists and to NASA. It's a challenging destination. It's a little sobering to realize that Cassini was the mission we had out there in the Saturn system, doing a number of flybys of Titan, giving us great pictures, and it dropped the Huygens probe, built by the Europeans, onto the surface, and that was in 1995. That was a very long time ago, and it gave back half an hour of data and of views of the surface and these amazing ethane-methane lakes and sort of surreal but almost terrestrial landscape. That was our last data from Titan, and it's been of extreme interest. So NASA is planning to go to Titan again, and the mission they have proposed or put a scheme together for involves this exciting Dragonfly technology. So the Dragonfly is a sort of drone system built for Titan. And remember, Titan has an atmosphere that's a little thicker than our atmosphere, in fact, made of nitrogen, almost pure nitrogen. And so we know how to design a drone for that atmosphere. And this drone would be flying around. It would have the base ship, the lander, would have more instrumentation and the telemetry and solar cells and so on, or a power source, nuclear power source. You're too far from the sun for solar energy, really. The Dragonfly helicopter, if you like, or drone, would be moving around the Titan surface, dipping into the lakes, hovering and sampling the liquid in the nearly frozen ethane-methane lakes, and bringing back to the main probe to biochemically test that, and then, of course, just to do a lot of imaging and scanning of the planet. So that's a very exciting mission. It's about 12 to 15 years off because it has to get a funding line, it has to be approved. It takes 7 or 8 years to get out there, a couple of years to do its work, and so these are long timelines. And it, in the outer solar system, sits behind the Europa Clipper mission, which has already got funding, and the Europeans are putting a lot of money into that too. All these missions are collaborative with the Europeans. It's so expensive to go to the outer solar system that the US and NASA can no longer go it alone. But that is an exciting mission. Enceladus is on the radar too, and it's sitting there in that top group, Europa, Titan, and Enceladus. It doesn't have a viable mission design yet. It would probably involve a lander, I'm pretty sure. But I've seen pure concepts out of NASA and other space institutes, but nothing that's even got close to getting on the funding envelope for NASA.
Thank you. The next question is from Lawrence, who's on with us live. If we assume that there are particles beyond the observable universe, are they moving away from us faster than the speed of light? And is this due to the inflation period after the Big Bang, or what's the explanation?
Yes, if there are regions of space-time beyond our horizon, which is to say there are regions that radiation or information or light could not have reached us in the age of the universe, then it depends on where they are and what the origination of them was. Even without inflation, so just taking the standard Big Bang into account, the early expansion rate was such that there are definitely regions of space-time beyond our horizon. And so these, we presume, are typical of our regions of space-time, with matter and dark energy and dark matter in them, and galaxies that are formed in them by gravity. So we don't imagine these regions beyond our horizon would be different. And they were indeed moving away from us at faster than the speed of light early on in the universe. The universe has decelerated, so some of those regions have entered our horizon, and we could see them now with our big telescopes. And then other regions, of course, have entered our horizon, and then acceleration has taken them back out again, or some of them were always beyond our horizon and acceleration is taking them even further away, so we'll never see them. So all of those things can be true. And what inflation does to this idea is just turbocharges it. So inflation expanded the infant universe in a tiny fraction of a second after the Big Bang by an exponential amount, 30 or 40 e-foldings of expansion from smaller than a proton to macroscopic sized. And that would have flung other space-time regions far, far beyond our horizon. And as the more slowly expanding universe by the Hubble expansion continued its growth, these regions are essentially never going to come into view. So they were moving, they were very superluminally, highly superluminally wrenched from our view, and that's pretty much the way they'll stay forever.
The next question is from Red Unleasher, who would like to know, what do you think are the odds of finding extraterrestrial life?
I think in the end the odds are very high, where we use life in the most general sense of the word, so any form of life. Microbial is the most likely, of course, because life presumably starts simple and gets complex given good conditions and sufficient time. And also, if we're being very general about our definition of life, where life need not mean biochemistry with the same basis as our biochemistry, which is to say nucleic acids and a genetic code that is the basis of all life on Earth. So if we're very flexible in that definition, given the ingredients that are out there in the universe, the number of habitable locations where there's energy, carbon-based material, a lot of time, and liquid water, then I put it as almost 100% the odds of there being life out there. Now that's the principle and easy to say, but the practice of it is much harder. So detecting it is hard, although we have some ideas. And it's certainly possible that if it's just rare, that it doesn't always happen. Say only 1 in 100 potentially habitable planets actually gets biology of any kind, then the nearest examples could be quite far. They could be hundreds of light years rather than dozens of light years. And that will make our astronomical attempts to sniff out that life by its alteration of a planetary atmosphere, for example, through photosynthesis, very challenging. So even if the odds of life elsewhere are essentially 100%, that doesn't actually guarantee that we'll find it soon or very easily.
And kind of a follow-up question to that, which do you sort of think is a better predictor of the odds of there being extraterrestrial life? Something like the Drake equation, which is mathematically, quote, correct but incomplete, or something like the Fermi paradox, which is more sort of theoretical but possibly accurate? Which do you think is a better predictor?
That's a good question. I don't actually think there is a good predictor of life elsewhere. The Drake equation is a useful formulation because it separates out the different aspects of the issue of life in the universe. So if we just accept that the product of a set of factors is as uncertain as the most uncertain factor, then the answer to the Drake equation is we have no idea, because the last factors of the Drake equation, the odds that given life it becomes intelligent, that given intelligence it gets technology, and how long it exists with that technology, those three factors alone, each of them is completely undeterminate. So the Drake equation is a logically and mathematically useful formulation, but it's not of any practical use at all, because the product of I don't know and I don't know and I don't know times three things you do know is still I don't know. The Fermi principle and question is attractive, but it's also not predictive either. The Fermi question of where are they really just arises from an extrapolation of our situation from the inference that life evolved on the Earth relatively quickly and has been on the Earth for 4 billion years, that a small extrapolation of our capabilities and technology should have us sending sentient probes around the galaxy, if not ourselves. And the question then arises is why would we be the first, and therefore where are they? Where are the other civilizations that have done this? So that's logically attractive, but it's not predictive either, because it doesn't tell you what kind of technology such civilizations might have had, what kind of probes they might have created. They could be completely microscopic. They could be atom scale probes, in which case we'd never see them. It doesn't tell you how they might communicate. The odds of us knowing that and interpreting that are also very low. And it also doesn't tell you how far away the nearest examples of a civilization might be. And if they're far, thousands or tens of thousands of light years, then we're operationally alone. And that becomes the answer to the Fermi question. So unfortunately, there's no, in a situation of uncertainty where the answers are given by observation, by experiment, we just have to do the experiment and hope we get lucky, or hope we find an answer, because the frameworks we're using for prediction essentially don't work.
The next question is from Abhishek Chabi, who sent an email asking, how can infrared light see through objects, and why doesn't it work with some objects like gases?
So infrared radiation has interesting attributes. I mean, it is essentially the same as visible light with just longer wavelengths. And all the different behaviors of infrared radiation essentially reflect its behavior. So we have to distinguish the behavior of infrared radiation relative to light through gases and through solids or liquids, because so with gases it's fairly simple. It really depends on what the size and density of the microscopic particles are. When there's a lot of small microscopic particles, they very efficiently scatter short waves of light. The waves of light are shorter than infrared waves, of course, and that for example is the Rayleigh scattering in our atmosphere that makes the sky blue. And in the interstellar medium, the near vacuum between stars, it's the tiny dust particles, 10 to 100 microns in size, that scatter and absorb that visible light very effectively. And that's why we can't see to the center of our galaxy, or even close to it. We can only see about 1,000 light years towards Sagittarius before dust completely extinguishes light trying to get out. Infrared radiation far less efficiently is scattered or absorbed by those same small dust particles, and so it travels freely, and that's why we see the center of our galaxy in infrared waves. So for gases and plasmas, it's fairly simple. It relates to the particle size. When you're talking about the way infrared radiation behaves with solids and liquids, it's more complicated. Then now you have to get into the business of materials. There's a famous or classic demonstration that people like me teaching intro astronomy or physics do in the classroom, where you show how infrared, use an infrared camera and show how it behaves relative for the long waves of invisible infrared radiation. For example, it can make images of people and shows the heat leaking from their bodies in the dark, but it also behaves differently with materials. So if you put a black polythene, like a garbage bag, over your hand or over someone's head, that's a dangerous thing to do. Obviously, you can't see your hand when it's inside one of those black garbage bags, but the infrared radiation does not interact with the polythene of the bag, and it's transparent, and so you see your hand. So when it comes to solids, glass is transparent to light, but it's a reflector to infrared. So behaviors of solids and liquids are very much dependent on their detailed properties, and you actually have to know that to see how the behavior goes. Out in space, it's a little simpler.
The next question is from Horatio, who's on with us live. In your book, Humble Before the Void, you indicate that in general relativity, there is no speed limit for the universe itself, and it can expand as fast as it wants. Can you comment on that and explain what you mean and why that is?
Sure, and I'm glad you read that book. It was not a technical book, of course, so I didn't really get into general relativity in detail. But what that means is that when the equations of general relativity were solved early in the 20th century in the circumstance of the cosmic scenario, or, as applied to a universe. The equations had two solutions. They either had contracting or expanding solutions. So general relativity applied to the space-time of the universe is a dynamic solution of expansion or contraction. These solutions were done by Alexander Friedmann, and not actually by Albert Einstein. I mean, he was aware of the work and he did those calculations too, but he wasn't first to do them. And so Friedmann used general relativity to essentially predict that if the general relativity equations describe the universe, it should either be expanding or contracting. That, of course, led Einstein to do what he claimed was the greatest mistake of his life, because having visited Mount Wilson in 1922 and been told the universe is static, not moving, not going anywhere, not expanding or contracting, because this is before Hubble's measurement of galaxy redshifts, he added a constant to the solution of his equations to suppress what would naturally be an expansion or contraction, the cosmological constant. If you do away with that blemish in the equations, you say, well, no, the universe should be dynamic, and so it is dynamic. And then the point becomes, what does the solution to the equation say about the expansion rate of space-time? And the answer is it doesn't have a boundary on it. So unlike the speed of light being a limit in special relativity, general relativity has no inbuilt speed limit to how fast space-time could be either expanding or contracting. And so there was no bound on that out of the theory. It's a matter for the observation. And then when you make a Big Bang model and apply the theory of general relativity to it, knowing what the matter content of the universe is and what the age of the universe is roughly, then you infer that the universe was expanding superluminally in the first third of its existence. And that's the model we have now.
Thank you very much. The next question is from Pekornin, who would like to know, how close could you come to Jupiter or any other gas giant without destroying the space probe?
Well, so Jupiter has it has an atmosphere, and it looks like a pretty clear surface when we see it from afar from a space probe that's hundreds of thousands of miles away. If you were actually to venture into it, and we've had ventures into gas giants. The Cassini probe, for example, famously did a death spiral into Saturn, the system it was studying, and Saturn's atmosphere is similar in scale to Jupiter's, and there's no hard edge, there's no sharp edge to the clouds. They just sort of gradually get more diffuse. So if you were to go into Jupiter's atmosphere, you just gradually see the density around you increasing and the opacity increasing until eventually you couldn't see back out into space. So, sort of like some cloud situations on Earth where the clouds are where there's no clear inversion layer and the clouds just are very diffuse, and you just gradually end up not being able to see back out of them. That's what would happen on Jupiter. And the temperature would be still very cold because you're still very far from the sun. You would have to go way into Jupiter's atmosphere, well past the point where the density was much higher than the density of the air we're breathing at the base of the Earth's atmosphere, before the temperature started to get warm. Jupiter is, however, superheated, so there's a point at which the atmosphere becomes extremely dense as a solid and very hot. And actually, since it's mostly hydrogen, there's a bizarre layer at the base of the atmosphere where the hydrogen is squeezed by enormous pressure into a sort of quasi-metallic form, a form that simply doesn't exist naturally on Earth. So the base of Jupiter's atmosphere is a bizarre state of matter.
Thank you very much. The next question is from one of our live viewers. Why is Uranus said to be colder than Neptune when it is much closer to the sun than Neptune?
Well, we're talking about the temperature of the surface, not the equilibrium. The equilibrium temperature, which is the temperature at the edge of the atmosphere, if you like, where the sun's radiation is received by the planet, that, of course, does go according to the distance from the sun, and the radiation temperature goes as the inverse square law of light. The complication that the question is alluding to relates to what is the temperature of the planet at its surface, because we believe the all the gas giants have rocky cores of 5 to 10 Earth masses. Their masses are not very well determined, and their sizes are not well determined. So it's just an inference, a pretty good inference, though, that they have rocky cores. And in the modeling, yes, if you, because of the nature of the circulation patterns and the density and size of the atmospheres and the planets, you do get this slight inversion where the planet that's further at its base of its atmosphere could have a hotter temperature than the planet that's further. And that's a little counterintuitive, but it comes because of the structure of the atmosphere.
The next question is from Jose, who's on with us live. Can you explain what a galactic eclipse is, and is it true that there will be one this year?
I'm actually not familiar with that term, so I may have to pass on that question, because I am not even quite sure what it might refer to, because the galactic eclipse obviously refers to the Milky Way or the galaxy we're in, and that's a big entity that doesn't have any obvious way to eclipse it, so I'm going to have to pass on that one.
All right, yeah, I didn't recognize it either. I thought maybe you would have an idea. It sounds like it's something that they should do a little bit of research on themselves. The next question is from Doctress Newtopia. What do you think of the possibility of solar power satellites and beaming the energy to Earth?
This is being increasingly well studied because there are certainly fairly robust engineering models of how to build very large solar collectors in orbit. You'd assemble them robotically in orbit. And so you could collect large amounts of solar energy in a sort of stable configuration, and then and use solar concentrators. And then the question is, how do you efficiently get it back to the Earth's surface? And the answer is you sort of turn it into microwaves, and so you beam high intensity microwave radiation back to Earth, and then have a receiver that'll store it, maybe in large batteries or something like that, put it straight into the grid. So you don't actually want to beam the sunlight itself straight down to Earth. It would obviously be very dangerous if anything got in the way. Well, so would the microwave, so none of this is trivial. So these are models that I've seen that could generate, many hundreds of megawatts with reasonably doable solar concentrators, and the microwave transmission technology is also fairly well established. And so it's a way to harvest solar energy without sort of putting infrastructure on the Earth's surface and taking land away from something else. So it's an interesting possibility. It's also a way of generating power to beam to other places, say such as a moon base, if you wanted to have power that you could flexibly purpose down to the Earth, or to a moon base, or to orbiting space stations, or the infrastructure we have orbiting the Earth. You could sustain a lot of your space infrastructure with a single, huge solar concentrator and collector.
All right, the next question is from Deba Parna, who's on with us live, and they'd like to know, is time quantized?
Not clear if it is quantized. In the classic theory of, obviously in Newtonian theory, it's not quantized at all. In general relativity, it's not directly quantized. It's, of course, coupled to space. Space-time continuum means that you can have metrics, you can have geometries and situations of space where the time axis is not orthogonal to space, where they become quite closely aligned, in fact. But that, again, doesn't speak to quantization. The quantization issue comes in when people are looking at these grand unified theories, the theories that go beyond unifying the three forces to include gravity in the equation. And since at that point you have to explicitly reconcile general relativity with quantum theory, it's very likely that you're going to end up with a quantized theory of gravity. So it's pretty much by supposition that a sort of theory of everything, if you like, will have to have some quantization applied to time, as it does indeed to space, to energy, to angular momentum, to everything else we measure.
All right, the next question is, do galaxies have constant size, or does their size change over time?
Galaxies evolve, and some of that evolution, that secular evolution, does involve their size. So the general scenario for galaxy evolution is the matches our view of hierarchical structure formation, which is a sort of bottom-up, top-down structure formation, where you start with the small objects. They form first and earliest in the universe, and then over time they merge to form larger and larger objects. We see this happening, of course. We see galaxy interactions and mergers happening out there in the universe. We can infer, piece together the stages of evolution that lead galaxies to merge and collide. We know the galaxy has had ingested dwarf companions, and we actually see evidence of it doing so right now with a couple, of which is very exciting to see that it's eaten dwarf galaxies very recently. And the result of all that, of course, is that yes, galaxies actually do grow. So giant ellipticals, built up from smaller pieces. The Milky Way probably suffered two major mergers, or two or three, a handful of major mergers with other smallish spiral galaxies, and then with probably dozens of dwarfs over time, including the handful that it's either consuming now or will consume in the future. So galaxies do grow. They do, however, reach a maximum size. So the maximum size and mass of a galaxy seen in the local universe or looking back in time, it is a particular number. It's about 1 trillion solar masses of stars. We've found no galaxies with more mass than that, and therefore no galaxies that are larger than about 200,000 parsecs across.
The next question is from Puneet, who would like to know, can gravity waves be used to produce some kind of anti-gravity propulsion system?
Well, gravity waves may have eventual uses. We're so early in our science of gravitational wave detection that our technology is barely able to detect them. The reason to be a little pessimistic about harnessing gravitational waves or gravity waves for an actual technology like you're asking in the question is that they're so incredibly feeble. So the gravitational waves that we've detected with LIGO and Virgo and continue to detect once every month or so from black hole mergers, these shift space-time or compress or stretch space-time by far smaller, like 100th or 1,000th of the size of a proton as the wave passes through. So it's a tiny amplitude, a tiny ripple in space-time, and that the energy deposited and the amplitude of the wave is so small that it's hard to imagine harnessing it for anything. So there are very speculative things. If we could somehow encounter much stronger gravity waves, what could we do with that? But we don't know astrophysically where such strong gravity waves might be produced or how we could harness them. So technology based on gravitational waves is very, very speculative in the future and pretty much science fiction at this point.
We've had a couple of people ask similar questions. So Arsh and Legit Gamers both would like to know, can you explain something about the God particle and what is the Higgs boson? So those are the same thing.
Right. The God particle, or the Higgs boson, is a centerpiece of what's called the standard model of particle physics, and it's sort of the capstone, if you like, of the standard model of particle physics, because it was predicted by theorists, Peter Higgs being the person it's named after. There were actually 3 other theorists involved, but he's the primary one, and he got a Nobel Prize for this. He's from my alma mater, University of Edinburgh. He's still there, retired and quite old, but still active. So the Higgs particle is the mechanism by which mass is attributed to all the other particles, and that's why it's the capstone of the standard model of particle physics, because the standard model of particle physics has all these hierarchies of particles. It has sets of heavy particles or baryons. There are 6 different flavors of quarks. There's up and down, which all neutrons and protons are made of, strange and charm, and top and bottom. And those are 3 mass scales going upward in mass or energy. And then there are 3 sets of light particles or leptons. There's the electron and the electron neutrino, the muon and the muon neutrino, and the tau particle and the tau neutrino. So three three light particles and their corresponding neutrinos, also going up in mass scale. And then there's a series of secondary and other particles you can make fleetingly in accelerators. And the question is, why are these hierarchies? Why are these families of particles? Where does the mass come from anyway? And the Higgs mechanism and the Higgs boson, it's called a boson because it's an integer spin particle, like a photon is integer spin, was the mechanism to attribute mass to particles. And rather than thinking of it as a particle, it's easier to think of it as a field, something that permeates space. And you could almost think of it as a viscosity of space. And certain things that we call particles interact more strongly with the Higgs field, moving through the vacuum of space. And that stronger interaction creates more drag, and so they appear to have more inertia and are more massive particles. Other particles interact more weakly with the Higgs field, and so they seem to have less viscosity, less inertia, and less mass. And so conceptually, that's the way to think about it, more as a field than as an individual particle. But in the theory, it does have a characteristic energy, and so the prediction was made back in the 60s and more accurately later that of the energy, which is about 130 giga electron volts, where if you had an accelerator, you would look to actually create this field in a concentrated form, which we call the boson or the particle. And it's called the God particle, nicknamed the God particle for, obviously tongue-in-cheek reasons, because it's a foundational piece to explain why mass exists in the universe. Otherwise, physicists had no reason to explain where mass comes from. They just counted mass, measured it, and looked at the patterns and were pretty much confused. So it was detected in 2012 and 2013 at CERN in Geneva as a very beautiful experiment with a Large Hadron Collider, sort of really justifying the construction cost of that huge accelerator. And it's a great achievement of theoretical physics to have explained in that one mechanism where the mass of all these different particles come from. However, a big asterisk by all of what I've just said, although the Higgs mechanism and the field and the boson and the particle, whatever word you want to use, is a successful mechanism to attribute different masses to different particles, it still doesn't say why there are three families of particles, why there's a hierarchy of masses, and why only three families and not two or four or five. So the Higgs doesn't explain everything. There's still some deep mysteries in particle physics.
The next question is from Pamela, who would like to know, with more and more powerful telescopes, will we ever be able to view the moment after the Big Bang? And if so, is that the same as seeing the center of the universe?
The telescopes we're building, especially if they're optical telescopes, are still going to be limited. So even the James Webb Space Telescope, working at more like near-infrared wavelengths, the largest ground-based and space-based telescopes are going to hit a limit at what we call first light, because there was a time before which there were no stars or galaxies in the universe. It's called the Dark Ages, and it probably lasted a few 100 million years. All the biggest telescopes that we can make in space or on the ground, working optically or in infrared, cannot go past that time because there was nothing emitting light. So that gets you to within a couple 100 million years of the Big Bang. So in a 13.8 billion year universe, gets you back to 13.6 billion years. Pretty good. If you want to get to the Big Bang, you have to do it different ways. The closest we've come in routine observation is, of course, the microwave background radiation, the relic radiation from the Big Bang that was released to travel freely through the universe 400,000 years after the Big Bang. That's a lot closer to the Big Bang than a few 100 million years. So the microwave background gets us very close. The closest we think we could get to the Big Bang indirectly is by looking for the imprint of gravitational waves on the microwave background from the inflationary era. And that has been proposed as a really important test of the inflation idea. Now, inflation is a mechanism that kicked in 10 to the minus 35 seconds after the Big Bang. So to have experimental, even indirect experimental verification that inflation occurred would be diagnosing a situation incredibly close to the Big Bang, as close as we could ever imagine. So that's very exciting. There was a false alarm over such a measurement a couple of years ago, where the polarization of the microwave background radiation was attributed to inflation, but it was a mistake. It was an error. They were confused by dust in the nearby universe. That measurement is being attempted by a set of microwave facilities in Antarctica and Chile and elsewhere. And it's very, very difficult, but probably will succeed in a few years, and we'll know, hopefully, whether inflation actually occurred. And if so, we will have had some insight into the incredible short time after the Big Bang, as close as we could ever imagine getting to it.
Thank you very much. The next question is from Bixtadub, who's on with us live. Is it dark matter that causes the variation in expansion rates throughout the universe?
I'll answer this question in two ways. The expansion rate in the universe doesn't vary with direction we look at. So even if that wasn't the question's intent, it's important to specify that when we watch the expansion of the universe looking out from the Earth in different directions, it could be the case that the expansion was anisotropic, that is, different rates in different directions, or had a different history in different directions. Until you do the measurement, the observation, you don't know. And so we've looked for that. So we've measured the Hubble expansion in the nearby universe, and then looked further out and seen the accelerating universe in different directions. And every direction in the universe, the history, the chronology of expansion and the nature of the expansion is the same. That's very important because it means the universe is isotropic. There's nothing special about one direction versus another. So that's one thing. Then the chronology of it is, of course, very important too. And yes, dark matter is a key factor in the chronology of the expansion rate, and so is dark energy. And in simple terms, the universe, in a pie chart sense of mass energy contribution to the contents of the universe is 2/3 dark energy, 1/3 dark matter, and 4 or 5% normal atoms and particles that we're made of. And so the expansion rate is essentially governed by dark energy and dark matter. Dark matter dominated the early expansion history, and that means the universe decelerated because the dark matter acted as a retarding gravitational force on the expansion that started with the Big Bang. But as the universe got larger, the dark matter was, of course, being diluted in space and spreading out over a larger volume, and so its gravitational effect diminished, whereas dark energy appears to be constant in time and space, and so its impetus, or its accelerating impetus, increased over time, and at some point about 5 billion years ago they crossed strength, and dark energy became more important than dark matter, and the universe has been accelerating ever since. So in simple terms, the universe was more dark matter dominated for the first 2/3 of its history, and so decelerating, and then in the last third of its history is dark energy dominated, and so is accelerating. And it will stay that way now forever, because the dark matter will continue to diminish in importance as the universe evolves into the future.
The next question is from Selva Surya, who would like to know, if life originated on a planet in a galaxy abundant with dark matter, what will their perception of gravity be? Would they derive the same laws of gravity? And what possible confusions might they have by observing galaxies without dark matter?
It's an interesting question. So I'll address how likely the hypothetical is to be truly the case in a minute. But if it were the case, if dark matter concentrations varied enormously from one galaxy to another, or from one situation in a galaxy to another, yes, it would affect how people made observations, because dark matter is the dominant gravitational component of the universe, and in a situation where it's even more dominant, the normal matter would be responding to the dark matter. Now, at the level of individual entities like humans or even planets or people, these distinctions are not very meaningful, for dark matter doesn't interact with normal matter, and so you would not be aware of dark matter being dense in your location as a person or as a person on a planet. But the structures you'd see around you in terms of how stars had clustered, and not at the level of solar systems even, but at the level of star clusters and the structure of the galaxy, yeah, it would make a big difference if the dark matter were very dominant. And so someone, intelligent human or an intelligent alien with astronomy knowledge on a planet in such a situation might really infer the dark matter dominance of their situation. If the dark matter were on very low level, that actually makes it unlikely that structure would form, because dark matter is the container within which normal matter clusters. And so if you had too little dark matter, you'd actually probably have a situation where structures didn't form, or stars didn't form, then planets didn't form, and then you wouldn't have anyone to observe it. So at that level, you're not going to see that situation. Now, the question of whether this actually arises is, in simple terms, no. It seems that as we've looked at galaxies large and small, near and far in the universe, many, hundreds, thousands, the fraction of their total mass that's dark matter is about constant from one location to another. There are a few situations where, due to interactions and mergers and a very bizarre history of clustering, the dark matter concentration is different. But generally, most galaxies have the same fraction of dark matter, so their circumstances are going to be very similar.
Thank you very much. The next question is from Aravind, who would like to know, what are tachyons?
Tachyons are hypothetical, faster than light speed particles. They are not in the standard model of particle physics, because in standard particle physics, particles are governed by special relativity, and in special relativity, if you try and by artificial or natural means, if a particle is attempting to move at faster than the speed of light, its mass increases. The mass increases as you approach the speed of light, therefore the inertia or the resistance to a change in the motion increases, and as you put energy into a particle to try and make it go faster than light, you're just putting mass energy into it, making it heavier and not increasing its speed. And so so speed of light is an asymptotic limit for any particle or any object for that matter. So tachyon essentially has to circumvent the limitation of special relativity by hypothesizing essentially a shadow set of possibilities where the particle is already moving at superluminal speed and then maybe accelerates from there, almost like a mirror situation to our special relativity governed universe. So since tachyons exist outside of special relativity, a very well tested theory, then they are entirely speculative. So you can conjure up a theory where tachyons exist, where they become part of some schema of as yet unobserved particles, but no one's ever seen evidence for them in 100 years of modern physics. So I would say we don't think tachyons actually exist.
Thank you very much. The next question is from Malik, who would like to know, when are we going to observe the next supernova explosion?
Well, any day now. I say any day now, any month now, any year now. As people know, as most people know, that we're overdue. We can observe supernova, the incidence of supernova. We know what makes a supernova go off, either in a binary star system, the type 1 supernovae, or in a single massive isolated star, type 2. So we know the progenitors of supernovae and how abundant they are, and the stellar populations. So for an object like a galaxy, you can make a fairly reliable calculation as to what the supernova rate is. And that number, it's not a super accurate calculation, but for our galaxy, the different people doing that get an estimate of about 1 per 50 or 1 per 100 years. That's the range of published numbers. So you expect a supernova of 50 or 100 years somewhere in our galaxy. Now, it might be on the other side of our galaxy, of course. It's unlikely to be very close to us. It's a big galaxy. But then you say, well, when was the last one? And the answer is 1604. That's over 400 years. That was Kepler's supernova. And Brahe had one 1572. So there were two in a short period of time, but they're both a long time ago. And there's a Crab supernova 1054 and a handful of others. So we are way overdue. Now, unfortunately, that doesn't mean something's wrong with the theory, because it's Poisson statistics. So that's sort of like saying if you are standing at a bus stop and the bus schedule says you should have a bus every 10 minutes and you're waiting there for 40 minutes, you cannot therefore infer that buses don't exist or that the whole bus system is broken down. No, something happened, or they're bunched and clustered and held up, and eventually one will come. So we've been waiting a long time, which means we're overdue, which really does mean it could happen any time. But of course, with Poisson statistics, it could happen in 10 years or 50 years or tomorrow.
The next question, again, is from a few different people. They have questions about white holes. So Legit Gamers, Aravind, and several others would like to know, is there any evidence that white holes exist? What are they? And if they do exist, why are we not able to find them?
So white hole is, again, a theoretical construct. I'll be very clear up front. There's no evidence for them. So that's the cold water I'll pour on the idea right up front, that astronomers have seen no evidence of white holes. In a theoretical construct, they would sort of be complements to black holes, places where energy was emerging from a singularity rather than disappearing towards a singularity. And so operational, whether they exist hypothetically in general relativity. You can make a mathematical construction in general relativity that has the attribute of a white hole as opposed to a black hole. You can read Kip Thorne's book about general relativity and black holes, which talks about it a bit. He doesn't also claim that he thinks they exist, but he acknowledges it as a mathematical possibility. And so then the problem becomes, well, how would you know it's a white hole? There are a lot of small regions of space where a lot of energy is coming out in our universe, and they're called quasars. They're the centers of galaxies where there's a supermassive black hole, and accretion onto that black hole heats up matter incredibly hot, blows out particles near the speed of light, and puts out a fantastic amount of energy. So from a distance, they might look like a white hole because it's a phenomenal amount of energy in a small space, far more than can be explained by stars. And so the question might become, if you're trying to look for a white hole, how would you distinguish it from active galaxies or supermassive black holes that are emitting energy by accretion power, or even smaller black holes emitting energy by accretion power? And that's really the problem operationally. So astronomers have not really considered the white hole possibility in general relativity compelling enough to do difficult observations that might try and find them, given that there are so many other things that might look like a white hole at some level.
All right. We started a little late, and we are ending. After about an hour, we'll have one final question, and then we'll wrap up for today. Arnold Ginsberg, who's on with us live, would like to know: is it possible to use our sun as a gravitational lens to see Earth-like planets? Frankly, to see anything.
Well, yes, our sun can operate like a lens in principle. So obviously the test of general relativity in 1919 was an eclipse expedition where the sun had bent the light from a star that was behind the limb of the sun by a small angle. And so that was an example of the sun doing lensing of a single star, deflection of the starlight. So you can imagine a geometry whereby an object well beyond the sun somehow has its light lensed by the sun. The trouble with that, and it can happen. I mean, you can conceive of a geometry where that is the case. The problem is it's a highly specific geometry. So the physical configuration that would lead the sun to act like a lens really only applies to a tiny angular and spatial region of space behind the sun. And the odds that there's anything actually there become very small. So the odds that the sun is actually doing this gravitational lensing are very small. Now, beyond the sun, astronomers have tried to think of more clever ways they could use objects in space, not the sun, but other objects in space, as natural gravitational lenses. And that there's been some success in doing that, but no one's managed to figure out how to do it for the sun itself. And thanks for your questions on all topics, as usual. very good range, and we'll be with you again next week. I can't remember the date, but it's coming up next week.
It'll be on the 18th.
18th, right. And thanks again to Alexander, the invisible Alexander, and Matthew for facilitating.